Okay, so I want you to hold on to your homework. I'm gonna talk about that first example. So the first thing is we've got to make sure we have the rate function right. So I'm showing negative 32x is the rate, the initial rate function. So if you want to make modifications to your homework, that's okay, but don't. The point of me going over this is for your understanding. Don't get locked into changing your work. So the key thing is you're listening and understanding. So rate function 32x. So I chose to do left sides, but I think I gave you the choice, right? You were able to choose whatever you wanted. So this is for left sides. So first, if you do the first 0.5 second interval, you're going to be 0 for that whole interval, right? Okay, so this is time for questions. Ask me questions if I lose you.
This isn't right. So when you say represent this as in terms of delta y delta x change actually, what do you mean by in terms of delta y delta x? So how do you want us to write that in the?
Maybe I'll get to that.
Okay.
So see what I do and then ask your questions. Okay. So yeah.
So that graph is just negative 32x.
Negative 32x is the rate. That's the rate at which this thing is falling because we wanted to find height. Positive is up. So if it's falling down, then that rate is negative because it's in the opposite direction of positive distance.
So your y-axis, that's height, and your x-axis.
No, that's not height. What's my y-axis over here?
Rate.
Rate. This is the rate. Rate on the left, and then we'll do height on the right. The accumulation of rate, accumulation of height on the right. Just like the rocket powered basketball. So just like the rocket powered basketball. But now this thing is falling, so its rate is negative. Okay? Next half second will be negative 16 for that whole half second. So I'm showing the blue steps is the step function. Next half second, 32. Next half second, 48. So since it's going down 32, the speed is increasing 32 every second, then it's going to increase by 16 every half second. So these are the rates. Any questions on the step function? Make sure you get it.
That's the left half of the interval, right?
This is using the lefts. That's right. Okay? And so then from there, yeah, James.
If you use the standard velocity formula and inverted the y and x-axis, do you understand the concept?
Maybe. I'd have to look at it. That's a pretty big change. So I'd have to look it over. Yeah. Okay? So, but standard is to have time on that, always have time on the x-axis. That's what conventional is. Okay, so that's the way you'll always see it, is to have time on the x-axis. Okay, so from here we can. So why do we change this very nice, realistic rate function into this step function? Why do we make it something that's not realistic? If we had the realistic rate function, that was a nice 32 feet per second increases every second. Why do we do that? We all should know the answer to this by now.
Because they have different rates of change.
What's that?
They have different rates of change.
What has different rates of change?
Every step.
Okay, but why do we do that? Why do we make the steps? Peter?
For convenience.
Convenience. Tell me more.
It's harder to calculate the slope of the good area underneath with the slope of the graph, so it's easier when you just have a straight line there.
Okay, it's easier to have a straight line. In order to do what? What are we doing? Mark?
It's easier to calculate constant rates of change than changing rates.
It's easier to calculate what using constant rates of change?
Yeah.
Yeah, so the bits of accumulation, in this case height, right? So our goal is to create accumulation. And so with constant rates, with each constant rate, we can get a bit of accumulation each time, right? But if the rate is changing, we have no way to do that. But actually, the whole point of this whole thing that we've been doing is so we can do that. Do you see? So we don't have an easy way to determine the accumulation for a changing rate, but that's our whole goal. So how do we do it? We do something we know how to do, which is we know how to get little changes in height easily if we have constant rates. So that's why we do this. So that first, and how is it that we do that? K delta x, right? In this case, K is our constant rate at any given half-second interval. Okay, so the first one, constant rate of 0 for 0.5 seconds gives a 0 change. Okay, then next one, constant rate of negative 16 for a half second means that it's going to fall 8 feet. Okay, and similarly, every half second, we use the rate and the step function to get the little change in height. And those little changes in height get bigger. Okay? And using this step function, it turns out that at exactly 3 seconds, it hits the ground. Using the left step function. Okay, so let me stop and see if there's any questions at this point. Yeah?
Yeah, so after, like at time 0.5, would it have changed 0, or when do you start? Like at 0.5 or 1 second?
Okay, so I'll throw that back at you guys. So ask your question. So are you?
So, like, I don't know. I set up my table like time 0.51, you know,
Okay.
and then just the change of height, I started it at 1, time second 1.
Because that was the first time it actually
Yeah,
changed.
so you start at 1, not 0.5? Or,
And then what was your
like
next?
so
in your-
I had it being a total of 3 seconds, like you had,
Okay.
so I think...
So after the 1, then by what increment did you go after the 1? Did you go by 0.5? So-
Yeah, I went by 0.5.
All right, so you just skipped that 1 because it didn't change.
Yeah, okay.
Yeah, it's fine.
All right.
Yeah. So, but I'm going to go ahead and show. Any other questions so far? Yeah. So because it didn't change in that first half second, he started with his first change at 1, but then he went by 0.5. Totally fine. Totally fine. But just to be thorough, we're going to show them all. Okay. So here would be then. This is a 1 representation of that accumulation function. That after 0 seconds, it's starting 120. After half a second, it's still at 120. After 1 second, 112. So now we start having our changes in height. Okay, so what was it falling? What did it say? A steel ball? A steel ball. Did it hover for half a second? And then start to fall? Okay, so why does this show that? Why does it show that for the first half second it just hovered at 120 and then it started to fall? Why? Janae?
Because your steps.
Yeah.
Starting from the left,
Okay.
and so really at 0 to 2.5 is when you start with 0.
Right. Is this based on the real velocity profile? No, it's based on this pretend profile, which is not realistic. The pretend profile means it doesn't move for the first half second. And so that's what's showing up here. Okay, so is this showing the ball always too high or always too low at a given moment? So look at our pretend rate function. What about how would this profile of the height changing compare to the actual way the ball fell? Oh,
Isn't it higher than the actually should be at?
okay, why?
Because one is starting point and not including actually.
Okay, so yeah, because okay, good. And then is that consistent through the whole thing? That in any half second period, what's our pretend rate versus the actual rate? Less negative, is that what you mean? Yeah, less negative. So then what would the actual accumulation graph look like if this, so you're saying that this is showing the ball always a little bit too high, right? Okay, so the actual accumulation graph is going to be a little bit lower than that. Did anyone do right sides? You did right sides?
Yeah.
Okay.
I actually ended up stopping at around 2.5 seconds.
Okay, and there's, why is that? So if you do right sides, what happens?
It started off at 0 and immediately drops to -8.
Right, so if you do right sides, I'll do it in black. Your first one will be here. And then you'll have here. And now what about the ball compared to the actual, if you'd use the right sides to approximate? It will be what? It'll be lower. Okay, so right off the bat, right off the bat, after a half second, you were down here. And then after 1 second, you were here. And then 1.5 seconds, you were here. Get that down. And then 2 seconds, you should have been here. And then something like this, right? So the black one is using right sides. Right sides means that the rate is always more negative or faster than the true rate, and so therefore the height decreases more quickly. So is there some real accumulation function or real height function for this steel ball? Ross, where would it be in this? How could you say where it is? The real accumulation function. Somewhere between, right? Somewhere between in this zone right here. There's an actual rate function, or sorry, actual height function for the given pink rate function. Is there a question?
I was about to ask if, like, you took the differences between the two lines, would that give you
Well, so something like that, like the averaging it out, only because, yes, that works in this case, only because it's a linear change in rate. So because there's a linear change in rate, well, let's think about this here.
like, did you
Not
just
necessarily.
average each section?
But averaging each section still makes linear pieces, and it's not going to fall in linear pieces. Okay. Yeah. So it's the right idea, but it doesn't do it because it's still that problem of a continually changing rate. Okay, so that's one representation of the left accumulation function, and then another one is our piecewise, right? So this would be, so this only gives the x values every half second. This gives every x value, right? So this piecewise version that we did gives every x value all the way. I left off the last line, right? So there should be one more line there. I left it off, so that line only goes to here. But this now, again, it will give you on that red graph that I've made, it'll give you every height for every x value, whereas this just gives you every 0.5. Questions on that? Anybody have a question? So I just want to take a moment to practice some meanings in this. This is a review from before. But this expression right here, so two expressions. I want you to, this expression right here, x minus 1.5. And then say this expression right here, negative 16 times x minus 0.5. So just want to quickly review. Do that one first and then this one. How would you interpret with words what the values of those expressions represent? So as a single value, that expression is a single value. So is the second one. In words, in this scenario of the falling steel ball, what is that first expression? What is the meaning of that value? And that second expression, what is the meaning of that value? So have a conversation. See if you can recall how to define those two things. Be specific. Be very, very specific. Here's the homework. Graded a long time ago. Go ahead. They do. For example, if x was 1.8, what would that expression equal? 0.3. So that's what you're asked. That's where you're interpreting the meaning of that value 0.3. For example, if x were 1.8, but x could be other things too. So, anybody think that they can interpret x minus 1.5? But somebody new, Christian.
Change in x,
Okay, specifically though, what change in x?
the change in x at that interval.
And what is x? So talk about the steel ball.
Okay, so the change in, I don't know, what's the time
Change in time
after 1.5.
after 1 point. Is that, you agree with that?
Yeah.
Is that what, Melody, is that what you're saying? The change in time after 1.5 seconds since we dropped the ball. That's what it is. That's what it is. Good. Okay. So what about the negative 16 times x minus 0.5? Molly.
What gives the change in y during the period of time?
And what is y?
Oh, the height, or how much it's traveled.
Okay. So it's the change in height. And so when you say during that period of time, which period of time?
From after 5 seconds.
Change in height since 0.5 seconds after we drop the ball. Okay? Good. Really important. Okay, so now this is where things get fun. What if there were 20 or 100 steps? Who, Ross or Gilbert? Say it louder.
So that would
I
suck.
said that would suck. Yes, right. Why would that suck?
Step function was close.
So let's just even go with 20. What will our step function look like?
Really long.
20 rows.
Yeah.
And what will our HX function look like? 20 rows, okay? So, but we've been building these tools. We're building all these little pieces so that today we're ready. We're going to be able to define step X as one rule. We're going to be able to do it. We've got all the pieces now. We just got to put them together. Okay? So this is pretty cool. Even if there are 100 steps, it'll still just be one rule. Okay? We do this today. And then, but our real goal is what? Our real goal is then, in order to get this as one rule as well. Okay, that's harder, but we need this one line, the one rule for step X, in order to do it. So we're going to define this accumulation function with one rule instead of how many steps we have, and that's our goal. Why? Because with graphing calculator, the number of steps is trivial. Right? It's just change the number of steps, and if we have a generalized version, then it just does it in a half a second. Okay. So does this make sense? What we're trying to do? So we want to be able to write the step function with one rule instead of a zillion. Okay. So let's go back to what we did last time. So I've kind of recreated, or this is that same thing we looked at last time. So I have a general, any rate function, Rx, any rate function, okay? And we have the current value of x, that's blue, so it's blue up in our picture, and it's blue here. And our goal is to figure out what the step function is. So we're gonna do it, we're gonna get lots of examples. So how would you, can you represent, say, what step x would be for the current value of x of 0.4? That's what's going to go there, representing. So we're just representing. Let me pause it, and we'll look at one particular one. So let's look at, let's come back here to say 1.2. All right, so here I'm at 1.2. Current value of x is 1.2. Question is, how do we represent step x? Okay, that's your small task here. How do we represent the value of step x when the current value of x is 1.2? See if you can do it. Oh, sorry. I'm sorry. I know you're going to go for those numbers. R can be anything. Okay, R can be anything.
Can you repeat what you want us to find
We're representing step of 1.2. So does that help? We're representing step. The step function could be anything. That scale up on the left on the axis could be anything. Okay? This R function can be anything. So how do we?
Are the intervals 0.5?
What's that?
Intervals of 0.5?
Yes, here. So it's right here. You're given Rx. Thank you. You're given delta x of 0.5 using left sides and a equals 0. So the question is, what is this right here? What is that value right there? Step x.
We're doing this based on the left side.
I'm sorry?
We're doing this based on the left side.
Just like the picture. So see how the picture's, yeah, left?
Just want to make sure.
Yeah, left side. So here's the setup. Let's see. How about Brian? What do you think? What is step of 1.2? Don't think you got it. Alexander?
So just plug in 0 for A.
0 for A.
Well, the equation is A plus rho function of x minus A over delta x times delta x. And I'm just plugging those numbers to get the left side.
Do we know what it is? Do we know what the left side is?
So I haven't calculated.
There's nothing to calculate here. I'm showing it to you.
It's 1.
It's 1. So what is step of 1.2? Is it 1? Shannon? R of 1. Steve?
Would be R of 0.2 or?
R of 0.2. Ooh, I'm glad I asked. Let's see, what else? Sterling?
R of 1.
R of 1. Chloe?
Yeah.
R of 1. Alexander? R of 1. So now we're getting a little more consensus. That's what it is. It's R of 1. That's what we worked on last Wednesday and Friday. It should make sense. The value of the step is the value of the actual function at the left side of the interval, and that's R of 1. Okay, so now what about R of 0.4? Mackenzie. Or step of 0.4. Step of 0.4.
A 0.4 is R of 0.5.
R of 0.5. Agree with that? Kevin, what do you think?
R of 0.
R of 0. Austin.
Yeah,
R of 0. Okay? Step of 1.3. Melody. R of 1. Step of 0.6. Ryan.
I'm sorry.
Sorry, I caught you off guard.
R of 0.5.
R of 0.5. Kaylin. Step of 1.6.
Be 1.5.
1.5? So the value of step is 1.5?
It's R of
R of 1.5, yeah. Okay, so which ones are R of 0? Ariana?
All the values after 0.5 to 0 and from 0 to 0.5.
So what about 0.5? Is that R of 0?
That should be all the values that are less than.
Yeah, so all those, right? So this is what we're showing. That all those values up to, but not including 0.5, so all through here, for all these current values of x, the value of the step is R of 0. Do you see? And then what happens at 0.5? Then what's the values of the step? Yep, all the way from starting at 0.5 up to, but not including 1, They are R.5. And then, starting at 1 up to 1.4 or 1.48, 1.49, everything up to but not including 1.5, R of 1, and then keep going like this. So that's what we're showing by this animation here. Where does the step function come from? Where do we build it? Where does it come from? In a word, in a simple word. Where does it come from?
The rate?
The rate function. It comes from the R function, right? We just got to get the right. We're going to get the correct x value, and we're going to use that x value at the left end and get the rate at that x value. So where does the step function come from? It's the R function. Okay, but so then we talked about. So notice that if x is 0.4, the step is R of 0. And if x is 1.2, the step is R of 1. So there's kind of like a middleman here, right? There's a middleman, and the middleman is the x value that we're plugging into R. So given the current value of x, there's some x value that we're plugging into R, and that goes in this row. It's the middleman. It's the middleman, okay? So for instance, at point 6, what's the x value that we plug into R? Just the value of 0.5, right? I'll do red here because that was our dots, right? 0.5. Oops. And then for 1.2, what was the value that we plugged into R for the step function at 1.2? 1. So these are the points, the left endpoints of the interval for the current x. Right, so we've got the current value of x, and then we did, from that we get the x value at the left end, and then we take the rate at that x value, and that's the rate corresponding to the current value of x in the step function. What function is that? This middleman. What function is that? What is it? Is it the floor function? The floor is part of it. The floor is part of it, but it's not just a floor function. What function is that function that, given the current value of x, spits out the left end of the interval? Russ? Yeah, left x. That's the one we built last week. So the floor function is involved, but it's not just the floor function. Okay, so how do we write step x in one line? So now we're given some r, x. We're using left sides. How can you write step x? Okay, so I want to think about it. So thank you. I appreciate but I want everyone to think about it and see if they can figure it out. So what does step x equal? We've laid it all out. How can you write step x in one line? See if you can figure it out. Take a minute or two. So the input is the current value of x. The input is the current value of x. The output is the value of the step function. All right, so I want to walk around and see what percentage of you think you have it. So if you want to talk amongst yourselves, or is the homework still making its way around? So show me what you think it is. Oh, pass in today's homework. Pass in today's homework. Hey, show me what you think it is. Show me what you think step x is.
So, just do something step.
You guys think you got it?
I just based that off. I don't know.
Okay, so we're at about 50% here. That's pretty good. Keep thinking about it. Okay. What do you think it is?
Yeah.
What is step X?
I googled it.
Okay, so we got some success. That's good. So what happens first? You take the current value of X and do what with it? What do you do with the current value of X first? You need to get left X, right? And what does that? Does the step function give us left value of X given the current value of X? No. What does? Left X. So we're going to put the current value of X into the left function, and it's going to spit out left X. And then what are we going to do? Then we're going to take that one and put it in Rx. Right? And what's going to come out? So, R of left X, or, sorry, running out of space here. So, R of left X. So the output of left X becomes the input into the rate function. So we're going to put in the current value of X. It's going to spit out the left. We're going to take that the X value at the left side and put that into the rate, and that'll give us the value of the step at the current value of X. Do you see it? Does it make sense? Anybody have a question? Is there a question? No. Okay, so we've got all the tools now. We can do this with graphing calculator, build a general step function. Any questions before we embark on that? Molly?
Wait, I was thinking left x equals step x. Is that wrong?
So, yeah, so step x, what kind of value is step x? What kind of thing is the output of step x?
No, but
What is it? Tell me. What is the output?
it gives you the y value.
It's a rate.
Yeah,
That's right.
it
What's
is
the
rate.
output of left x? What kind of value is the output of left x? An x value, right? So that's a really good question, okay? So what goes into left x? The current value of x goes in, and what comes out of left x? An x value or a y value? Another x value, the one at the left end of the interval. What goes into step x? Current value of x, and what comes out? A rate, right? A constant rate. Constant rate comes out, or a y value in the rate function. Okay, good. So here's your task. Open up a blank window in Graphing Calculator. See if you remember everything. I'm giving you the outline, but I want to see if you can do it. I'll make that bigger. So here's the outline for graphing any general. So the first thing you want to do is define the rate function. It can be anything, okay? Define R of x. So it can be changeable, right? Changeable, starting at any value a. And today we'll use e to the cosine x, all right? So if we're all doing the same thing, we'll use e to the cosine x, but then r can be changed easily, right? Just by changing the rule. That's the first step. We want to graph the rate function for x greater than or equal to a. And again, a is changeable too, right? define our slider. It doesn't have to be called delta x. So if you've got a PC, you can use dx or write out the whole phrase delta x. All right, make it a variable. So we want to have that delta x be a slider so we can change that interval length. Okay, we want to plot the endpoints of the intervals. You did that for homework. Maybe we need to review that. But then you're going to define the left end function. We worked on that last week. And now today we know how to do the step function and we graph the step function. So everything we've done. So I want to see how much you remember and how much you can do it on your own. So if you don't have graphing calculator in front of you, if you can share with somebody, it looks like most of us do. But find someone to share with on that. Okay? Let's see how you do. Is the task clear?
Whatever. We have to put oh, but we're defining.
Can you guys switch places?
Next one. Because we're gonna put a.
So here's how we want to do this. So don't use if, use comma, and then we're going to define, say, a equals 1, okay? So that's how we can start. So you're defining the function and the starting value on the same line, and those are both changeable. We can just go and change the rule. For the rate function, we can change that starting value there. Okay, I'll let you keep going. Questions? Where'd you get lost? Graph. What do we graph? Graphs. What tells us graph? Goal 2, right? So there's something that will initiate and tell the graphic calculator, I want to graph this on the axes, right? Y equals. So you're going to do graphs. That's really nice.
You have to define a variable before your
You can do it. Order doesn't matter. Order won't matter. So you want to start this is the graphic. You want to show it for x greater than a. Remember how to graph a function. We worked on that. Y equals.
Of course, I took out.
How's the graded homework making its way? Did everyone get the graded homework stack? You want to see that? Where's the rest of them? The leftovers? Just one. Okay, thank you. Any more of today's homework? Did I get all of today's homework? Question? So you just define your parameter, whatever it is, equals, right, just write slides. So to do a slider, you're gonna pick whatever your variable is gonna be. So as a character string, you gotta use the backslashes, or as a single parameter is fine. You could use like D, and then you say equals slider. No, other way around. Sorry, slider equals your variable.
Oh, what is that? Wait, can you do that?
Yeah, I'm gonna do it again. You got to start with slider. Slider. No, what am I doing?
You got our backslashes?
Why am I flailing here? Delta x equals.
You have to use capital X, I think.
Here we go. So we got our parameter equals slider. But the comma should have come up. No, because slider is built into graphic calculator. When you type slider, it knows what you mean. So we're going to start at 0 and go to 1. There we go. And when you finish it, it should pop up. No, that's not a function. It's just parentheses. It's an operation or something of graphic calculator that it knows. Is everyone able to get the slider to pop up?
You gotta define it first.
Yeah, it's a variable, just like you've got to define that thing as a single variable. So if you're going to do a character string like delta x or more than one character, you've got to use your backslashes. Does everyone get on that?
Yeah.
Okay, so were you able to get your endpoints? So this was the little task at the end of the homework. End of the homework, Control 2. So we want those points to be, what I told you to do was do for J a member of 0, 1, dot. This was all in your homework. So how do we get, if we're going to let J go from 0 to 100, how do we get those points on the x-axis, like those red points I've got on the x-axis? So what's the y value first of all? Okay, good. Got half of it done. So 0. So how do we get, what are the x values starting at A with an interval width of delta x? How do we get those x values? Did you figure it out? Steve?
Yeah, I put x as a, and then where you put the 0, I put a, and then the next one, a plus delta x.
Yeah, so what, in the J thing?
Yeah.
Yeah, I was trying to, in one of the specifications and then the video, I tried to tell you, leave it 0 to 100
Oh, okay.
and put your formula in the point. So how did you put the formula in the point? Did anyone get it? Control 2. Oh, the braces is a member of, that was in your homework, control equals. Control equals. And then the braces are shift bracket. Okay, so someone's going to offer up. Alexander.
I put A plus.
A
Delta X.
plus delta x. Just like that? Is that going to give us, so that's just going to give us 1 point, right? We want all the points. A plus delta x 0 is just going to give us the right side of the first interval is equals 1 point for us. Yeah, so j, then we want times j. And we want those in red. I want to put those in red because that's the way we've been doing it, those points. So we can just graph now and see if that we've got our rate function and our points at this point. Uh-oh. Oh, because my delta x is 0, right? So make delta x 1, change delta x to 1 with the slider, and it works. Where did I lose you? I'm sorry? Yep. That, so... Other questions right now? Yeah, Aaron.
Yeah.
How do you get the as a member of NPC? Control Shift E, thank you. Other questions? Oh, I don't want to go any further until you guys are school. So what have we done so far? We graphed the rate function and we got our endpoints on the x-axis, our red points. Yeah? Ellipses.
Control semicolon.
Oh, the dot dot dot?
You need to like
Control semicolon. Okay. All right, so we only got 2 minutes. I want to see if we can get this done. Okay, next, define left x. So we need, but it's going to be a character string, so left, control 9, x, and we know this one, right? A plus, to get the floor function, you just type floor. And we want x minus a, this is what we worked on last week, all over.
I did all this and it didn't cut off my graph. Like at the points, like the points are there. Just pause it for the most. It didn't cut the graph.
I can look at it. I can look at it in a second. Okay, that was our left x function. What does that do? That takes any current x value and what's that function spit out? The left value of the interval. Yeah.
Wouldn't the two delta x's cancel out? That doesn't make sense.
So we worked a couple days on understanding that formula, so we can talk about it in office hours. Yeah.
How do you do the floor function?
Just type floor. If you type floor, it just pops up. Okay? All right, now we're ready for the step function. So we define the step function. Again, you need a string. Wow, I'm flailing here. Okay, step, and that's what we did today. What, oh, man. Control 9, x. How do we get step x? That's what we did today with this table. R, control 9, of, left, control 9, x, right? Take the current value of x. Left x gives you the left x value. We put that into the rate. It gives us the step is. And then we want to graph it. Y equals step x. And we want to graph that for x greater than or equal to a. And let's do it black.
Do you need to not be able to graph?
Which other graph? No, you want them both. You want to see them both. Okay, but there's an issue, right? This doesn't look like what we did. What's the problem? Obviously, this is not looking like what we did. So what does graphing calculator do? It doesn't know what the function is. It just has a way of rendering it by taking lots of points and connecting the dots. So what are we seeing here? At the end of this, there's a point, and then suddenly there's a point down here, and so what did it do? Connected the dots. So we want to show everything except we don't want to show the x values at the left endpoints. So what we can do is take care of that. We can do y equals step x if x does not equal, what do we want x not to equal? Anything else is good, but x doesn't equal what? To get rid of those endpoint lines, those vertical lines. Left x. So it's at those periods where the current value equals the left value where we're getting that vertical line. So if we remove those, we want all other points, then it should go away. There it is. Okay, I understand we're a little bit over, so if you need to go, you need to go, but I'll walk around if you want help getting yours to work. I can stay around. Yeah.
Thank you.
Yeah.